Hi, I'm Yukio Kawashima. I'm a quantum computing application researcher at IBM Tokyo Research Lab. Today, I'm going to talk about the methods of quantum chemistry simulations. In the introduction, I'm going to show you what quantum chemistry simulations can do, and then I'm going to talk about the Schrodinger equation and Born-Oppenheimer approximation to show you what kind of equation we want to solve in quantum chemistry simulations. And next, I'm going to talk about the quantum chemistry methods. The quantum chemistry methods that I'm going to talk about are shown on your hand side. I'm going to talk about the Hartree-Fock method, semi-empirical methods, correlation methods, which include perturbation theory, configuration interaction, coupled cluster methods, and density functional theory. I am going to also talk about the basis sets we use in quantum chemistry simulation and atomic orbital integrals we compute in the quantum chemistry simulation. To understand all this in just 2 hours is extremely difficult. So therefore, the goal for me today is to give you an insight of what quantum chemistry simulations are doing. By the end of the talk, I hope you'll be more interested in quantum chemistry simulations, and hopefully you'll be willing to run quantum chemistry simulations on your own. Now I'd like to start the introduction. What can we do with quantum chemistry simulations? The first example is tackling the chemical reaction. So the chemical reaction goes from left to right, and the vertical axis is showing the energy. So the chemical reaction starts from this reactant formaldehyde molecule, and it goes through the transition state and end at the product. So the product here is the hydrogen molecule and the carbon monoxide molecule. By using quantum chemistry simulation, we can calculate the energy of the reactant, transition state, and the product. By doing so, we can calculate the energy difference between those states. We can calculate the activation energy and the reaction energy. The activation energy corresponds to the barrier height the reaction needs to overcome to go on forward. So if the activation energy is too high, it's likely that the chemical reaction will not occur. If you have multiple pathways and evaluate the activation energy of each reaction, then you could investigate which chemical reaction is more favorable than the others. You could also create a new chemical reaction pathway on your computer using quantum chemistry simulation. Next, you could also tackle molecular properties. The molecule on your left is the beta-carotene molecule. And the figure on your right is the computed absorption spectra of this molecule using quantum chemistry simulations. This axis is showing the excitation energy, which is energy gap between the ground state and the excited state, which also corresponds to the wavelength of the light to be absorbed by this molecule. And this axis is showing the intensity of the spectrum. So you see a large peak here, which ranges between purple, violet, and green. So the violet, blue, green lights will be absorbed by this molecule. And the remaining yellow, orange, and red lights will be reflected. So that's why this beta-carotene's color is orange. We can use quantum chemistry simulation to investigate various molecular properties. And also we can create a new molecule in our computer, and by tuning the properties and functions of the molecule, we can create a new molecule with a function of your desire. We can also tackle molecular dynamics using quantum chemistry simulation. A colleague who was a gas phase experimentalist came to me and said, look, I have a molecule here, and it forms a hydrogen bond with a water molecule, which is hydrogen bond, by the way, is a weak bond. And if this molecule forms a weak bond, the hydrogen bond, with a water molecule in this location and this location. So there's two locations which forms a hydrogen bond with a water molecule. However, when I ionize this system, the water molecule forms a bond only here. So there's only one location. So if I start from a neutral state molecule with a water molecule here, what will happen if I ionize this system? In an experiment, they found out that the water molecule starts from here, but end up here. But they don't know what's happening in between. So that's why my colleague came to me and said, can you use simulation to investigate what's happening in between? So I performed molecular dynamics simulation of that system. And so first I ionize the system and see how the dynamics will go. So the water immediately detaches from here after ionization, and it wanders around and forms a hydrogen bond with a water molecule here. And it's a bit interesting to see that the water always goes in this direction, not in this direction. And depending on the trajectory, it folds around sometimes, but it always ends up here. So what that means is that using quantum chemistry simulation, we can investigate something that cannot be observed in experiments. So you see that quantum chemistry simulation can be extremely powerful. So quantum chemistry simulation is also called electronic structure calculation. It solves the distribution of electrons in molecules. Various static properties can be computed using quantum chemistry simulation. And also, we can understand motions of molecules using quantum chemistry simulations as well. The typical static properties we can compute are shown on your right-hand side. So we can compute equilibrium geometries, and we can calculate the barrier heights and investigate the reaction pathways of chemical reaction, as we did in the first example. And also we can compute spectra. The second example was showing you the result of the absorption spectra, but we could also compute the NMR chemical shift, the circular dichroism spectra, the infrared spectra as well. We could also compute electronic properties such as dipole moment, the polarizabilities, and so on. And also we can compute thermodynamic properties. So quantum chemists use the quantum chemistry simulation to investigate the properties of molecules or investigate various chemistry problems. But not just that, also researchers doing experiments also use quantum chemistry simulation. What they do is that they use quantum chemistry simulation to interpret their experiments. Especially if you have data of spectra, it'll be really convenient if you use quantum chemistry simulation to interpret your spectra. So quantum chemistry simulation is not just important for quantum chemists. Nowadays, it's also important for other chemists as well. So you see, quantum chemistry simulation is a very important tool. Well, now I'd like to move on to the next section. So I'd like to talk about the Schrodinger equation and Born-Oppenheimer approximation. And I want to show you what kind of equation we want to solve in quantum chemistry simulation. First, I'd like to show you the time-dependent Schrodinger equation. So this is the time-dependent Schrodinger equation. Here's the Hamiltonian, which has the kinetic term and the potential term. And psi is the wave function. So you can see that the Hamiltonian, the potential energy term in the Hamiltonian, and the wave function, they all depend on space r and time t. And if you see the left-hand side of this equation, you see the first derivative of the wave function against time. So what this equation is describing is, it's describing the quantum system evolving in time. So by solving this time-dependent Schrodinger equation, you can solve the propagation of the wave function. This time-dependent Schrodinger equation is a partial differential equation. Note that we here do not consider relativistic effect or spins. Next, I'd like to show you the time-independent Schrodinger equation. So here is the equation. Now the Hamiltonian, which again has a kinetic term and a potential term, and the wave function, psi, only depend on space, r. It doesn't depend on time anymore. We solve this time-dependent Schrodinger equation when we're interested in the time-independent problem, such as the quantities in equilibrium. So in time-dependent Schrodinger equation, you solve it when you're interested in the time-dependent problem, of course. So in the case of quantum chemistry, we're interested in the time-independent problem. The Hamiltonian is time-independent. So we're going to solve this time-independent Schrodinger equation. This time-independent Schrodinger equation is an eigenvalue equation. So if we solve this equation, we get the eigenvalues as total energy and eigenvectors as the wave functions. There's a small n here, but what it means that by solving the time-independent Schrodinger equation, we could get multiple roots. So what that means is that we can calculate the ground state, and not just the ground state, but we could also compute the excited states, which are above the ground state. So we could get multiple roots. Today, however, my talk is focusing on the ground state. So in most of the equations, these n are dropped off. But please remember that if we can solve time-independent Schrodinger equation, we could get multiple roots. We could get not just the ground state energy, but we could also get the excited state energy as well. Now I'd like to move on to show you the molecular Hamiltonian. Here we assume that our molecule has 2 nuclei and 2 electrons. The nuclei are shown in this large red circle. Nucleus A with mass Ma and charge ZA, and nucleus B, mass Mb, it has mass Mb and charge ZB. And the small particles here are the electrons. They're labeled with the lowercase letters. Oh, the nucleus are labeled with the uppercase letters. And electrons I and J here has the mass of small m and charge of -1. So there are 5 terms in the molecular Hamiltonian. The first 2 are the kinetic term, and the latter 3 are the potential term. I'm going to look into the terms one by one. So the first term here is the kinetic energy of the nuclei. The uppercase A runs through all the nuclei. And in this molecule, it runs from A to B. The second term is the kinetic energy of the electrons. So the lowercase letter I runs through all the electrons. And in this case, it runs from I to J. The third term is the nucleus-nucleus repulsion, which is shown here. The AB runs through all the nuclei, and I'm just this is to avoid the Defog counting. And if you see this, this is actually the electrostatic potential between the nuclei. So 4 pi epsilon naught and RAB will be the distance between the two. And on the numerator, we have the ZA and ZB. So here you can see that it's the electrostatic potential. And the fourth term is electron nucleus attraction. What I mean by attraction is that the charges are the opposite, so they attract with each other. So large A runs through all nuclei, and small I runs through all the electrons. And you see there's 4 pi epsilon naught RIA with one lowercase and one uppercase letters. And those interactions is shown here. RIA, RJ, RJA, RIB, and RJB. They all belong to the electron nucleus attraction. Again, they are the electrostatic potential between the electrons and nuclei. The last term is the electron-electron repulsion. In this figure, it's shown here. Again, it's 4 pi epsilon naught with the distance of Rij, and it's E squared. So it's the charge of 2 electrons. And this runs through, Ij runs through all electrons, and again, avoiding the double counting. So these are the 5 terms of the molecular Hamiltonian. Now I'd like to introduce the atomic units. In atomic units, the reduced Planck constant, the mass of the electron, the charge of the electron, and 4 pi epsilon naught for the electrostatic potential are all 1. So this Hamiltonian I showed you in the last slide is now like this. It's more simple. By the way, I use the same MA here and here. However, it has a different meaning. This MA is a relative mass from the electrons. In quantum chemistry simulation, there are cases that we deal with Hamiltonians, which has relativistic effect, or Hamiltonian considering spin orbital coupling. However, in the talk today, I'm not going to consider relativistic effect and spin orbital coupling. Now I'd like to move on to the Born-Oppenheimer approximation. So nuclear mass, which is Ma here, is very large compared to the mass of the electrons. So electronic motion is extremely fast compared to the nuclear motion. So now we could have an approximation here. So we can assume that the motion of electrons can be decoupled with the motion of nuclei. So we could freeze the nuclei. And Born-Oppenheimer approximation mostly works in most of the chemical problems. However, there are exceptions. One example is a conical intersection. At conical intersection, the ground state and the first excited states are very extremely close. In this vicinity, the nuclear motion and electron motion couple strongly. Therefore, in this case, the Born-Oppenheimer approximation breaks down. However, in most cases, a Born-Oppenheimer approximation works. So therefore, in quantum chemistry simulation, we apply the Born-Oppenheimer approximation. So here was the molecular Hamiltonian, and let's see what happens to the Hamiltonian after applying the Born-Oppenheimer approximation. So, as I mentioned, we could freeze the nuclei. So the kinetic energy of the nuclei can be removed. And also, the nuclei can be treated as classical point charges, and the nuclear coordinates will be fixed. Therefore, here, the nucleus repulsion term. This will be a completely classical electrostatic potential, and this will be a constant, so we don't have to explicitly treat this term when we solve the problem. It'll be just a simple shift in the energy. So then we could determine the electronic Hamiltonian after the Born-Oppenheimer approximation. So this will be the electronic Hamiltonian. The first term will be the kinetic energy term of the electrons. The second term will be the electron-nucleus attraction. And the last term will be the electron-electron repulsion. So we only have 3 terms. And by the way, I've introduced this showing that the nuclear coordinate r will be fixed. Now I'd like to discuss about the electronic wave function. The wave function psi is like this. So I mentioned that I was not considering the spins previously, but now I'm going to introduce the spins. In addition of the spatial coordinates x, y, z, I will introduce a new coordinate here, which is omega, which is the spin coordinates. So for each electron, I have 4 coordinates. So x1, y1, z1, omega 1 for electron 1, and x2, y2, z2, omega 2 for electron 2. The square of psi is the conditional probability for finding electrons at the given coordinates. And this electronic wave function needs to satisfy another condition. That is the antisymmetry against the exchange of electrons. So what that means is that if we exchange electron 1 and electron 2, like this, here we have electron 2 here and electron 1 here. It has to change signs. So this is the antisymmetry against the exchange of electrons, and our wave function have to fulfill this condition. Now we have the electronic Hamiltonian and electronic wave function. So we can determine the electron Schrodinger equation we want to solve. So in quantum chemistry simulation, we are solving this electronic Schrodinger equation. So the Hamiltonian will be the kinetic term of the electrons, the nucleus electron attraction, and electron-electron repulsion. So by solving this Schrodinger equation, we can compute the electronic energy, shown here and here. So we have another term actually, the nucleus repulsion term, which I mentioned that it's fully classical. So we can calculate separately from this, solving this electron Schrodinger equation, and add it afterwards as a shift to the energy. And the total energy is the sum of this electronic energy and the nucleus repulsion term of the energy. This total energy is also called the potential energy, which depends on the nuclear coordinates. If you have any experience of running quantum chemistry simulation before, maybe you have seen an output showing the electronic energy and the total energy. The electronic energy is the energy you get when you solve this electron Schrodinger equation, and the total energy is the energy adding these 2 terms. So next, I'm going to explain what I mean by potential energy depending on the nuclear coordinates. So what I mean by the potential energy depend on the nuclear coordinates. For instance, if I have a system like this, a diatomic system, and in this molecule, we only have 1 internal degree of freedom, which is the interatomic distance. So suppose I calculate the electronic Schrodinger equation with 1 bond distance, and then I change the bond distance little by little and calculate the electronic Schrodinger equation again and again and again. And if I plot the energy it'll be a smooth curve like this. This surface constructed by varying the nuclear coordinate is called the potential energy surface. So if you see this potential energy surface, the x-axis is interatomic distance, and the y-axis will be the potential energy. So you see the potential energy is a function of the interatomic distance here, which is actually the nuclear coordinates. So that's what I mean by the potential energy depends on the nuclear coordinates. And this is the potential energy surface, but since we have only one internal degree of freedom in this molecule, which is the interatomic distance, we call this a potential energy curve. The potential energy curve or surfaces have a lot of important information. For instance, the minimum of this potential energy curve is showing the most stable point, which has the equilibrium geometry here. So this is the optimal bond length of this molecule. And if you shorten the bond length, the atoms will feel the repulsive force, and it'll be more the molecule will be more unstable. And if we elongate the bond distance, then the interaction will be reduced. And at a certain point, these two atoms will not feel each other. So the energy will converge to an energy of A plus B. So the energy difference at the energy of the dissociation and energy at the equilibrium geometry, the difference is the bond energy. So what that is that it's the energy the molecule gains when it forms a bond. So you see, you could find a lot of important information in the potential energy surface. So I showed you this slide in the first example of the introduction. I vaguely mentioned that this was the energy, but this was actually the potential energy. And I just vaguely mentioned that the reaction goes into this direction, but it was actually along the reaction coordinate, which depends on the nuclear coordinates. So I was just showing you the potential energy diagram along the reaction coordinate. So if I write a potential energy surface of a reaction, I'll get a potential energy surface like this. So here is the reactant, the most stable point, and the transition state, the maximum, and the product state, the minimum. For all 3 points, they will be at the stationary points in the potential energy surface. What do I mean by the stationary points is that V is the potential energy, and its first derivative against each internal degree of freedom is all 0. So they're all 0 for these 3 points. And the reactant and the product, you can see that they're at the minimum of the potential energy surface, while the transition state is at the saddle point of the potential energy surface. The saddle point is that all but one, for all degrees of freedom except one, it'll be at the minimum, while at 1 degree of freedom, like this, it'll be the maximum. This is the saddle point. And we can distinguish the minimum and the maximum using the Hessian matrix. The Hessian matrix is a second derivative of 2 internal degrees of freedom. And if we construct this Hessian matrix and diagonalize it, for a minimum, we'll get all eigenvalues as positive. And at the saddle point, we'll get one eigenvalue is negative, and the remaining all other eigenvalues as positive. So these are the stationary points in the potential energy surface. Last of all, in this section, I want to talk about the molecular dynamics simulation I showed you in the third example of the introduction. Maybe some of you might thought that the molecular dynamics is dynamic, so it's a time-dependent problem. Why aren't you solving the time-dependent Schrodinger equation? If I was treating the nuclear motion quantum mechanically, yes, you're right. However, I am applying the Born-Oppenheimer approximation. So the nucleus, I'm only going to treat the classical effect of the nucleus as a point charge. So the nuclear motion is classical. So therefore, I'm not going to solve the time-dependent Schrodinger equation. I'm just going to simply solve the classical equation motion. However, the nuclei are feeling the force from the electrons around them. So that is the reason why I want to treat the quantum effect from the electrons. Therefore, I'm performing the quantum chemistry simulation to calculate the force from the electrons on the nuclei. And the force, of course, will depend on the coordinate of the nuclei. The electrons and nuclear motions will be completely decoupled. So I was moving the nuclei little by little using molecular dynamics simulation, but what I was doing was I was monitoring the dynamics along the potential energy surface. I hope it makes sense to you. So I've talked about the Schrodinger equation and Born-Oppenheimer approximation in this section. I talked about time-dependent Schrodinger equation, time-independent Schrodinger equation, and Born-Oppenheimer approximation. Now I think you know what kind of equation we want to solve in quantum chemistry simulation. We want to solve this electronic Schrodinger equation. And I also talked about the potential energy and potential energy surface. Next, I'd like to move on to talk about the quantum chemistry methods. I'm going to talk about the Hartree-Fock method, semi-empirical methods, correlation methods, which include perturbation theory, configuration interaction, and coupled cluster methods. And last of all, I'm going to talk about density function theory. So let me start from the Hartree-Fock method. So as I mentioned, we're going to solve the electronic Schrodinger equation, and here is an electronic Hamiltonian, which has the kinetic energy of electrons, nucleus electron attraction, and electron-electron repulsion. The last term, the electron-electron repulsion term, is the most difficult term to deal with. So we want to make this a bit more simple so it'll be more easier to solve. So the underlying idea is the mean field approximation, or we could also call it the independent particle model. So of course, each electron feel each other in a different way. However, we could introduce an approximation such that each electron feel the other electron as an average field. If we can introduce that, this will become like this. So this will be sort of an average potential, and it will be a one electron operator. So as you can see, the kinetic term of the electrons and the electron nucleus attraction term, they are both one electron terms. So if we can make this a one electron term, all the terms will be one electron terms. So it'll be far more easier to solve. So hopefully we could do this. So this is the underlying idea of the Hartree-Fock method. Next, we'd like to consider the wave functions that we're going to use in Hartree-Fock method. So first, we consider describing the wave functions as product of orbitals. So first, we have the wave function here, which has four coordinates, x, y, z for space, and omega for spin. And we're going to combine all these r omega to x, a new coordinate. So our spin orbital has chi, and x is a coordinate. The two-particle wave function then can be described as product of orbitals, which is psi x1 x2 equals chi1 x1 times chi2 x2. And if we exchange the two electrons, it'll be psi x2 x1 equals chi1 x2 chi2 x1. But if we describe our wave function as product of orbitals, these two will be the same, so it won't be antisymmetric against exchange. As I mentioned to you, our wave function has to satisfy the antisymmetry against exchange. So this idea won't work. So we can't treat our wave function as product of orbitals. So we need a better strategy. Instead, we could describe our wave function as Slater determinants. So this is a two-particle case, and this is the Slater determinant for the two particles. We can calculate this easily. So chi1 x1 times chi2 x2 minus chi1 x2 times chi2 x1. Like this. So it'll be like this. And if we exchange the particles now, then if you check it, you'll see that the sign will be flipped. So if we describe our wave functions as Slater determinants, the antisymmetry against exchange will be satisfied. So we can write it in a more general form for n particles. This will be the Slater determinant. And from now on, I'm going to write the Slater determinant in this form. In Hartree-Fock, we will describe the wave function as a single Slater determinant. So we want to solve this electronic Schrodinger equation, but it cannot solve this analytically. We have to solve it numerically. And we could do so by employing the variational principle. So here is the function, the risk function we want to minimize using the variational principle. This is shown here. So the numerator here is the expectation value of the Hamiltonian, the electronic Hamiltonian. It could be also written like this. And in the denominator, what this is, it's overlap with wave functions. So if we normalize it, it should be 1. So minimizing this function is equivalent to minimizing this expectation value under the constraint of this being 1. The variational theorem assumes that the true ground state will be the lower bound. So what we can do is we can minimize the energy by varying the parameters or varying the wave function or optimizing the Slater determinant. So we can minimize the energy by doing so. So we can put the trial wave function in it and repeat it until the convergence criteria this will be fulfilled. And here is the Hartree-Fock energy expression. The first term I introduced this new operator, which is shown here. It is the kinetic energy and electron nuclear attraction for electron I. So this integral is actually the expectation value of the kinetic energy and the electron nuclear repulsion for electron I. So this term runs through all the electrons. How about these terms? These are the two electron integrals. The first term is the Coulomb term, and the second term, the exchange integrals. So I want to show you what these are in the next slide. So now I'd like to show you what the two electron integrals are. So the first one is the Coulomb integrals. So if you see this carefully, it's chi I star x1 times chi I x1. So this, you could see that this is the density of electron I. And again, if you see here, it's chi j star x2 and chi j x2, which is the density of electron j. And we have this 1 over r operator, so what that means is we're calculating the electrostatic potential between electrons I and j. I think this is easy to understand because this has a classical counterpart. So we have an electrostatic potential with 2 point charges. It's the same as that, but here we have a distribution, so we're going to calculate the electrostatic potential between the densities. How about the exchange integrals? It's very similar, but you see that j here and I are swapped. This exchange integrals, they arise from the anti-symmetry against exchange. So these don't have any classical counterparts, they're purely quantum. Since they originate from exchange, we only treat exchange integrals with the same spins here. While the Coulomb integrals, we consider both opposite spins and same spins. So these were the 2 electron integrals. By minimizing the Hartree-Fock energy, which I just showed you, with respect to the orbitals, we arrive at this Hartree-Fock equation. So this epsilon is the energy or eigenvalue of a spin orbital, and chi I is, of course, the spin orbital. And H is the one electron term, which is the kinetic energy of the electrons and electron nucleus attraction. And here you see a term here, which is showing the electron density of electron J here. So you see, this is a contribution from the Coulomb integrals. And this is also quite, it looks similar, but here you see that the spin of the index of ij are swapped here. So this should be the contribution from the exchange integrals. So I'm going to introduce 2 new operators, j and k, which are here and here. These 3 terms will have a more simpler form like this. Note that how this k operator works is that if the k operator acts on chi I, it'll be swapped to become chi j. So this is a result of chi j operator acting on chi I. That's what it means. So, and then we have this simple form of equation, which we saw in the mean field approximation slide. So by using the Slater determinant as a wave function and using the variational principle, we arrive at equation just the same we saw in the mean field approximation. So we're indirectly introducing the mean field approximation here. So then what that means is that it should be easy to solve. However, it's still difficult at this moment because we have the integrals here, and we also have a differential in the kinetic energy term. So it is an integral differential equation, and it is yet difficult to solve. So we have to do something extra. So we will introduce another concept, which is the linear combinations of atomic orbitals. So here is the spin orbitals, and we're going to describe these spin orbitals with the linear combination of atomic orbitals chi bar. They're also called the basis sets. So what we're going to do here is that we're going to perform or carry out the integrals using the atomic orbitals. And if we carry out the integrals first, then we could get the simple matrix form here. So what that means is that by introducing the atomic orbitals, we can convert the problem into pseudo eigenvalue problem. Here, the eigenvectors are the molecular orbitals C. They're also known as the molecular orbitals coefficients. And we also get the eigenvalues, epsilon here, which are the molecular orbital energies. So now we finally have the equation that we can solve easily. And by the way, we can't solve this in one shot because if you remember in F, we have this chi and the j and k operators. So what that means is we have C also in F. So we need to solve this iteratively. So that iterative procedure is called self-consistent field procedure. We start from the input of the 3D coordinates, the atomic nuclei. As we mentioned, the potential energy depends on the coordinates of the nuclei. And we also determine what kind of atomic orbitals we'll use. Then we will construct the initial guess of the molecular orbitals, and afterwards we construct the Fock matrix. And then we diagonalize it, so at this point we get a new C, the molecular orbital coefficients. And if it's converged, we terminate the calculation, and if not, we go back to 3 and repeat this process until the convergence is fulfilled. So at the end, we get the optimized molecular orbitals and Hartree-Fock energy. So what we mean by molecular orbitals are optimized is that we get the linear coefficient of the linear combination to form molecular orbitals using the linear combination of the atomic orbitals. So we can construct this, the molecular orbitals here and here using these atomic orbitals. And C is showing the suitable coefficients for the linear combination. So here we have talked about the Hartree-Fock method. So in Hartree-Fock, we use a single Slater determinant as the wave function. The variational principle will be used to calculate the minimized energy. The parameters will be in the wave function, and we'll optimize the parameters to get the suitable Slater determinant. This introduces the mean field approximation where each electron's field other electrons as an average field. We also introduced another concept, the linear combination of atomic orbitals, which helps our problem become a pseudo eigenvalue problem. And I also explained about the self-consistent field procedure we use to perform Hartree-Fock calculation. So now I'd like to move on to the next part of my talk. So I'm going to talk about the basis sets we use in quantum chemistry simulation and atomic orbital integrals that we compute in quantum chemistry simulation. So first, I'd like to talk about the basis sets. What are the basis sets? The basis sets are the functions for representing the atomic orbitals that describe the electronic wave function. So we construct the molecular orbitals using these atomic orbitals. There's several types of basis sets. The first one is the Gaussian basis sets. They're frequently used in quantum chemistry calculations for isolated molecules. The second one is the plane wave basis set. They're used in calculations for extended systems, such as crystals, metal, semiconductors. There's also a real space basis sets, such as finite element and wavelets. In quantum chemistry simulation, we mostly use the Gaussian basis sets. So today, I'm going to talk about the Gaussian basis sets. And if we can increase the number of Gaussian basis sets, we get more accuracy in our calculation. However, we are increasing the computational cost. So it's the accuracy versus computational cost trade-off. So here is the general form of the Gaussian function shown here. And here I'm not using chi because they're simply spatial orbitals. They don't depend on spins. So I have phi and psi. So we're gonna form the spatial orbitals psi using the linear combination of these phi's. So this is the Gaussian function, and x1, I, yi, and zi are the center of the Gaussian function. Typically, we choose the center of the nuclei as the center of the Gaussian function. And in Gaussian basis sets, the predefined parameters are this and this. So they're determined based on the atomic properties. So it only has information of that. It doesn't have any other empirical information in it. And as I mentioned, if we have more number of basis sets, we can get our computational results more accurate. However, we don't want to increase the basis sets as much as possible because we're increasing the computational cost. So we want to make our basis more flexible, but we do not want to increase the number of C. What can we do? We can introduce this contracted basis. So we only have one phi. The number of phi won't change, but we can define this as a linear combination of a couple of Gaussian functions. So in this case, also, dij is a predetermined parameter based on atoms. By doing so, we can increase the number of bases while not increasing the number of the coefficients to optimize. There are several different types of basis sets. One of them are the minimal basis sets. It's using the minimal number required to represent all electrons on atoms. The famous one is STO3G basis set. The next one is a split valence basis sets. It represents the valence orbitals by more than one function, while it treats the core orbitals using one function. So in chemistry problems, the valence orbitals play an important role compared to the core orbitals. So that's why we won't use more functions for the valence orbitals, while we won't use much for the core orbitals. So that's the idea of split valence basis sets. The famous ones are the pole basis sets, and the 631G star, or like 6311 plus G star star. And what does star mean? Star is representing the polarization functions, which have the higher angular momentum. I'll talk about this later. But what's the difference between star and star star means that the first star means that it's going to apply the polarization functions for the heavy atoms, such as the atoms in the second row, like carbon or nitrogen or oxygen. And if you have star star, the second one means that you're gonna introduce the polarization functions to light atoms, which is hydrogen. We also have a term plus, which means the diffuse function. The diffuse functions are functions which have the small alpha here. So we have more of a widely spread distribution. These are frequently used in molecules such as anions, where they have more of a widely spread distribution compared to the neutral species. There are also correlation consistent basis sets, which are systematic basis sets for conversion correlation methods to get very accurate results. The famous ones are the CCP, V, and Z. So what CCP V and Z means is if it's D, CCP V DZ, it means that you're using two functions per AO, atomic orbital. If it's TZ, you're using three functions for each atomic orbital. And if it's QZ, it'll be four. And if it's P5Z, it'll be using five functions for each atomic orbital. Yeah, these are the quite famous ones in quantum chemistry. So I also want to explain what SDO-NG or 631 means. So here is the form. Here is the form of the contracted basis. And sorry, I mistyped here. This should be around here, but it's okay. So first, about the minimal basis sets, there's an expression called SDO-NG. What that means is that we are trying to make a one Slater type orbital. So we're going to make one orbital here with using n Gaussian functions. So we want to use n of these functions for making this function. So SDO3G again means we're going to build this one orbital of one basis set using n number of contracted basis sets. And for the split valence basis sets, there is a term like 631 or 6311. What is that? The first 6 is describing the number of contracted bases for our core atomic orbitals. So in split valence basis sets, we only use one function, one of this, to describe the core atomic orbitals. But we're going to use 6 of these to describe one of this. That's what 6 means. And how about the next numbers, 31 or 311, what that means? So 31 has 2 numbers and 311 has 3 numbers. So what that means is that for the former, we're going to use 2 bases to describe the valence atomic orbitals. And if it's 311, we're going to use 3 basis sets to describe the valence atomic orbitals. So that's what the number, that's what's 31 or 311 means. But how about what actually 3 or 1 means? It means that we're going to use 2 bases as we mentioned, but we're going to use 3 of these for the first one and 1 of these for the second one. And for 311, that means we're going to use 3 of these contracted functions for the first one, 1 function for the second one, and 1 function for the third one. That's what 31 or 311 means. I hope you understand what these mean now. Now I'd like to move on to angular momentum. I mentioned that there are cases that we need to use basis sets of higher angular momentums, so I want to discuss what I meant by that. So here is the basis set we have, and Lx, Ly, Lz are the angular momentum for each x, y, and z. So here, this figure is the solution of the Schrodinger equation of hydrogen atom. These are the hydrogen orbitals or the atomic orbitals you get by solving the Schrodinger equation of a hydrogen atom. And for L equals 0, you have this S-type function. For L equals 1, you have a P-type function. And for L equal 2, you have a D-type function. And L equal 3, you have F-type functions. And as the number of L increases, the number of nodal planes increases as well. So here you have 1, here you have 2 nodal planes, and here you have 3 nodal planes. So if we are dealing with hydrogen, for instance, we usually only need s orbitals because we only have s orbitals filled in hydrogen. However, what we want to do here is that we want to describe the molecular orbitals accurately as possible using atomic orbitals. So in that sense, sometimes using atomic orbitals of higher quantum numbers will help describing the molecular orbitals accurately. So that is the reason why we use p functions or d functions, even d functions for hydrogen as well. So we use orbitals of higher angular momentum to make our results accurate as possible. Now I'd like to move on to show you why we're using Gaussian functions. So here's one of the advantages using a Gaussian function. So first advantage is the Gaussian product theorem. Suppose we have two Gaussians in 1D. So we can combine this to make it to a one Gaussian function with a prefactor. If you see the prefactor and if you look at mu and x, you see they are all fixed values. So this will be a constant. So we have made two Gaussians into one. So that's one advantage. And the second advantage is the recursion relation. So here's a general form of the Gaussian function, but x, y, and z are separable. So why don't we just focus on x? So x is a form like this. So of course, by definition, this is quite obvious. So GL times x minus x should be, of course, GL plus 1. But what this means is that if we calculate G with lower angular momentum, we could use the recursion relation to compute the G of the higher angular momentum. And also, if we once calculated G, then we can easily calculate the gradients shown in this recursion relation form. So what this means is that we can calculate both gradients and also the Gaussians with higher angular momentum easily using the recursion relation. So this recursion relation is the second advantage. So now I'd like to move on to talk about integrals computed in quantum chemistry. We're going to talk about integrals in atomic orbitals. So again, this will be the Gaussian atomic orbital, Gaussian basis set. And we're going to use this to compute the 1 electron integrals and 2 electron integrals. So the 1 electron integrals has a kinetic energy term of the electrons and electron nucleus attraction term. And the two electron integrals have the electron repulsion term. And as an example, we'll try to compute this. So let us assume that we could start from the very simple Gaussian function. So we should have a value of Lx, Ly, and Lz, but let's start by considering the simplest Gaussian function, where Lx and Ly, Lz equals 0. So this will be a very simple Gaussian. And we are going to apply the same thing to all Gaussian functions, mu, lambda, and sigma. And then we can use the Gaussian product theorem and combine all these Gaussian functions. And then we'll get this equation. So the first part here, 2 pi, is something, K1 and K2. K1, if you see this, K1 will be depending only on the parameters, fixed constants of mu and nu, is shown here. So this will be all constant. So K1 will be a constant value. And again, K2, depending on the parameters, the constant values of lambda and sigma. So again, this will be the constant value. And same goes for P and Q. P and Q. So now they're all constants. So this is a constant term. And how about this term? So F0 alpha R PQ squared. The general form of this function is the incomplete gamma function shown here. So this is the function we will want to evaluate the integrals. And by evaluating this integral, we can compute this integral. And once we get this, then we could get the integral values of this function using the recursion relations. So we're going to first use the Gaussian product theorem and make it simple to compute. And then we're going to calculate the incomplete gamma function. And then we're going to use the recursion relations to get the values of high angular momentum. So I talked about the basis sets and atomic orbital integrals. So first I mentioned about the basis sets and I focused on the Gaussian basis sets. And I talked about the advantage using Gaussian basis sets, the Gaussian product theorem, and the recursion relations. I also talked about atomic orbital integrals, and I just very briefly show an example of how we calculate the two electron integrals. So this is the last slide of the first half of my talk. There is a term called ab initio molecular orbital methods. So I showed you the Gaussian basis sets, and I mentioned about the predefined parameters based on atoms. Besides that, we have no empirical parameters in our calculation. So therefore, we call it the ab initio molecular orbital methods from the start. And they include the Hartree-Fock method, which I showed you, and perturbation theory and configuration interaction and coupled cluster methods, which I'm going to show you later on. These are the ab initio molecular orbital methods. And on the other hand, semi-empirical methods include empirical parameters, so they are not ab initio methods. And there's also density functional theory, and it's first principle, and some people actually even say that it's ab initio, but it's not ab initio molecular orbital methods. It's a completely different concept. So, well, I think it's fair not to include density functional theory in ab initio molecular orbital methods. Okay, so I guess this is the midpoint of my talk. So let us take a break and I'll stop sharing my screen and I will pause the recording. Let us have a break.